right, we're going to look at the assignment 301.4, Balanced versus Unbalanced Forces problem set, and walk through the questions. Number 1 says, if the forces acting upon an object are balanced, then the object, and you have some choices here, must be moving with a constant velocity, must be accelerating, must not be accelerating, must not be moving. Okay, when the forces on an object are balanced, that means that they all cancel out, or maybe there aren't any there in one direction and they cancel out just in the other. But regardless, according to Newton's second law, which again states F net equals m times a, if you have those balanced forces, that means your net force is 0. And if your net force is 0, then mathematically your acceleration will also have to be 0. Zero acceleration could mean that the object is moving at a constant velocity. It could mean that you're moving at, let's say, 5 meters per second, and that it's not changing, because acceleration is rate of change in velocity. So if you are moving at 5 meters per second, and you're still moving at 5 meters per second the next second, and then still 5, still 5, still 5, that is an example of zero acceleration. But it's not the only example of zero acceleration. Another example of an object that is not accelerating is an object that is not moving. An object that is at rest would, of course, also be experiencing zero acceleration. So it isn't necessarily moving with a constant velocity, and it isn't necessarily not moving. Okay, it says must be, must be. Those are not true statements. If they said could be and could be, they would be true statements. The only thing here that is absolutely going to be true is that if the forces are balanced, the object must not be accelerating. It could be moving at a constant velocity. It could be not moving at all. Regardless of which of those is true, it will not be accelerating. Question number 2 says, a spaceship in frictionless deep space fires its engines for 3 seconds, which describes its motion at the end of the 3 seconds when the engines are turned off. Again, F net equals ma. If you fire your engines, you're applying a net force and it will cause acceleration, and now you have a rocket that's moving. Okay, again, let's use just some fake numbers. If it started at rest and you turned on the engines, okay, so velocity at time 0 is 0. You turn on the engines after 1 second, maybe it's going 5 meters per second. After 2 seconds, maybe it's 10. After 3 seconds, maybe it's 15. So long as you are applying a force and you have a net force, acceleration is going to happen. This change is going to happen. However, once the engines are turned off, so let's say right here, the engines get turned off. Now your net force is 0. Now you're no longer accelerating. And so again, no longer accelerating doesn't mean you stop. Okay, in fact, if they were to stop from here, that would be accelerating. No longer accelerating means the velocity doesn't change. So it would be 15, 15, 15. It would be 15 the whole time. And so what that would mean is that until it ran into something or some other force made it stop or speed up, it would maintain a constant velocity when the engines are turned off. And so the answer to this is it moves at a constant speed, because there would be no net force acting on it when the engines are turned off, because we're in space. There's no friction, there's no air resistance, there's no gravitational forces, there's nothing there. There is no more net force other than the engines. And if the engines are off, you're not going to accelerate. And that would mean that you're moving at constant speed, unless you weren't, of course, unless you weren't moving at all. But they're moving if they fired them first. So moves at a constant speed. Question 3. We just saw these diagrams in the last assignment, 301.3, but here they are again. And it says, according to the free body diagrams above, which of the objects could be moving to the right with a constant velocity? Again, could be are the key words here. Well, 2 of the key words. The other one is constant velocity. So we're looking for a situation with constant velocity. As I just mentioned in the last couple of questions, constant velocity simply means that we're not accelerating. Okay, this was a constant velocity, 0 acceleration. And so you're looking for something where you have 0 net force, because those objects could be moving at a constant velocity. You need ones that cancel out. The ones that cancel out are going to be this first one, A, this third one C, and that's it. These other two don't cancel. So these two would accelerate. They couldn't be moving at a constant velocity. These two could be moving at a constant velocity, but what about the words to the right? Okay, could they be moving to the right? And the answer to that is yes. Looking at these free body diagrams, we don't actually know which way these objects are moving. There is not enough information here. We don't even know if they're moving. But again, it says could be. These two could be moving to the right with a constant velocity. For the record, any of these could be moving to the right. But the only ones that could be moving to the right at a constant speed are A and C. All right, so we have the same diagrams again for number 4. Okay, so same diagram, and it says, according to the free body diagrams above, which of these objects would be accelerating to the right? Again, this time we're looking for ones that are accelerating, and again, if I have acceleration, I have to have a net force. In order for this to occur, we have to have a force here. Okay, and so we can't pick the same ones we did in the last question. They can't be balanced here. In fact, in order for them to accelerate to the right, their net force has to be to the right. And so looking at these diagrams, the only ones that have a net force to the right are B and D. Okay, those two both have a net force, and that net force is in the rightward direction because that vector to the right is longer than the vector to the left. Or this one doesn't even have one, but B and D. Question number 5 says, a skydiver is descending with a constant velocity. Consider air resistance. Draw a free body diagram below for the system consisting of the skydiver and parachute together. Okay, so we're looking at these two as a group, and I know that if I'm going to be descending at a constant velocity, I know that the forces that I draw acting on my skydiver parachute system need to be equal and opposite. Otherwise, I won't be constant velocity. Again, for constant velocity, I need a net force of 0. So I know that this skydiver parachute system has a downward force of gravity. There is a weight to them. I know that it tells me to consider air resistance, and so I know that I have air resistance in the upward direction. Air resistance is basically friction with the air molecules, and so I know that I'm going to have to include that as well, and I know that I need to draw these in such a way so that they're the same length because it tells me constant velocity up here. Those are the only forces to consider. I did have some students ask about the tension in these ropes, but because it says that the system is the two of them together, that tension is inside the system. It's not acting on the system. We're looking for the forces that are acting on the two of them together, and that's the air resistance and the weight. If you had been asked to draw the forces acting on the skydiver himself, then there would be tension here. But since it told us to include the parachute, we're not going to include tension. Gravity, air resistance, my net force, I don't have one. That's the point. If you see these words, constant velocity, your net force should be 0. Number 6 is about Timmy. Timmy has fallen in a well. Firefighters are rescuing Timmy by securing him to a harness and pulling him upward. Timmy considers his situation as he is being pulled upward at a steady speed. Which statement below most correctly describes the situation? I know this isn't math, but it is asking us to kind of compare some forces in here in these questions. So I'm going to go ahead and draw a free body diagram anyway. Okay, it is a helpful tool to help me analyze the situation. Okay, obviously Timmy is on Earth, and so I know that there is a force of gravity, Timmy's weight. However, he is being pulled upward. He has a harness, he's attached to a rope, and so I know that there is a force of tension upward. Before I finish drawing this vector though, I need to think about how long to draw it. Should it be shorter, longer, or the same length? In the question, it says that he is being pulled upward at a steady speed. I'm going to assume that means constant velocity. And so I'm going to draw my force of tension, Ft, so that it is equal in opposite to Fg. Okay, because that's the only way we're going to get that constant velocity is if our forces are balanced and we have a net force of 0. So from that, now I can take a look at these questions. The first one says, which statement below most correctly describes his situation? The first one says Timmy is accelerating with gravitational acceleration. This would be true for the portion of the motion where he actually fell into the well. When he was falling, he would be falling with gravitational acceleration. He'd be in free fall. But that's not the situation now. Now he is attached to this harness and this rope, and so there are other forces acting on him. He's no longer in free fall. Since he is moving at a steady speed, Timmy is at rest. Okay, being at rest would not be moving with a steady speed. I guess technically you can maintain a velocity of 0, but that is not what's happening here. It says he is being pulled upward at a steady speed. That implies he is not at rest. The third one says Timmy is not accelerating. Again, that steady speed does imply that we're not experiencing acceleration. The last one says he's accelerating upward. He is being pulled upward. But again, velocity and acceleration are two different concepts. He can be moving upward at the same speed the whole time. To accelerate upward would mean that he's getting faster and faster and faster as he is being pulled upward, and that is not what is described in this scenario. So although he is moving upward, the way this is worded, he is not accelerating. The second part of the question says, which statement below most correctly compares the tension force pulling him up with the weight pulling him down? And that's why I drew the diagram. Okay, in my diagram, I can already see it. The tension force is equal to his weight. And again, I chose that because of those two words. He is being pulled upward at a steady speed. Constant velocity means balanced forces. It means 0 net force and thus 0 acceleration. And 0 acceleration means constant speed or at rest. But in this case, it means constant speed. The next question says, a 22 kilogram bookcase is pushed with a force of 211.4 newtons so that it accelerates at a rate of 9.61 meters per second squared. Is noticeable friction present in this scenario? Okay, this isn't exactly the same as the questions that we've done in class. This one's going to require you to think a little bit. Okay, and I did ask you a question in class about how friction affects acceleration. So before we even look at these numbers, if there is friction present, okay, let's say there's friction present and I'm pushing something, okay, I would expect that in the presence of friction, the acceleration of the object I'm pushing is less than the force that I am using. It gives me a smaller value than I would expect based on the force that I'm using. If friction is absent, like if I removed the friction, well, now that acceleration is going to be greater because there's no longer friction working against me to reduce the acceleration. Okay, so what we need to do is we need to figure out if the acceleration in this question, this 9.61 meters per second squared, is that the acceleration you would get based on this force and this mass? Okay, because this is how hard you're pushing, 211.4 newtons. And if that's the only force there, that would mean there's no friction. Okay, so let's look real quick and see what we get based on that. What acceleration do we get if we use, and again, I'm going to go back to the F net equation, if my net force is just that one number. And again, I don't know if it's true or not. That's the whole point of the question. Is there friction? I don't know. Okay, so I'm going to take my 211.4 newtons and I'm going to say maybe this is my net force. I actually don't know. That's what I'm checking right now. Okay, my mass is 22 and I'm going to see what acceleration I would expect. If I push this hard and there isn't any friction, I would expect some amount of acceleration. If I calculate this and I find out that it's 9.61, then I know there isn't any friction here. But if I get something smaller than 9.61, then I know that there has to have been friction present to make this smaller than it would have been based on that alone. Okay, so 211.4 divided by 22, 9.61. Okay, that's basically what that says. And so no, there is no friction here because the acceleration I just got assumes that all of the force that was used, this 211.4 newtons, all of it was used to make that acceleration happen. There wasn't anything slowing it down at all. No other forces at play, just that one. And so that would mean there was no friction present. Second question. If the same bookcase is then pushed with the same 211.4 Newton force across a different surface and experiences an acceleration of 2.7 meters per second squared, what is the coefficient of friction between the bookcase and this new surface? Again, the acceleration when there wasn't friction, so without friction, my acceleration was 9.61. This second question tells me my acceleration is only 2.7. Again, I can tell already there's friction here. There has to be, because I used the same force, but now there's a lot less acceleration. So there's a pretty significant amount of friction that's causing that number to be smaller. Okay, and so now we're going to figure out what that amount of friction is. So again, we're kind of having to work backwards. Again, this is making you think a little bit. Okay, so second part of the question, I know my force, okay, my applied force is 211.4 newtons. I know there's friction though. There has to be. I don't know what it is yet, okay, but I know that there's friction. All right, so I know that. I know the acceleration is 2.7 meters per second squared. Okay, I know it's the same bookcase. So let's go back up real quick because we had a mass up here. So I know that mass is 22 kilograms. So I know the mass. I know the acceleration now when I'm on this new surface. Okay, so with these two pieces of information, I can figure out what the net force acting on the bookcase is. I know that that net force is going to be the result of friction and the applied force kind of working against each other. Okay, so that's what we're about to do, is solve for the net force. All right, so I can solve for that by simply plugging in my mass, 22, times my acceleration, 2.7. So 22 times 2.7, is 59.4. So my net force, F net, is 59.4 newtons. Okay, and my net force will be in the direction of my applied force because it is, friction cannot be greater than this. Your force of friction can only ever be less than or equal to that force that it's opposing. So at the most, this could be 211.4, but if you have a net force, this is smaller than this. All right, so I have my net force, and I know the applied force. I can solve for friction, but it would really help if I drew a diagram of this first so you could see how I'm doing that. So I have my object. I have my applied force. It doesn't actually mention directions anywhere in here, but let's go ahead and just say that my applied force is going this way and that it is 211.4 newtons. I know also that I have a force of friction going this way. Okay, and I know the net force, or the sum of those two forces, is 59.4 newtons. So I know this one is 59.4 newtons larger than that one. But again, I can write that equation out. My net force isn't just equal to MA. My net force is also the sum of my forces. In this case, I'm only looking at the horizontal forces. There are vertical forces occurring here, okay, but I don't need them for this part of the question. I can go ahead and draw them though. There is the force of gravity, and there is a normal force acting on this object because it's being pushed across a surface. I do know that these are equal and opposite to each other, so I can go ahead and include them, but I don't need them for this part of the calculation because there is no net force in that direction. So I'm going to say my net force in the x direction horizontally is the sum of my forces, FF, plus this force here. And again, keeping in mind that forces are vectors, this is in the positive direction, 211.4 newtons. And I should have put my net force in here because I know that number too. That number is 59.4. So 59.4 is equal to FF plus 211.4. So if I want to solve for force of friction, I'm going to I'm going to subtract, these are being added, I'm going to subtract 211.4 from both sides. So 59.4 minus 211.4 gives me negative 152. So that is my force of friction, negative 152 newtons. Now that is not actually the answer to my question, because the question doesn't say what is the force of friction. Rather, it asks for the coefficient of friction. Okay, the coefficient of friction is mu, and it shows up in this equation. Force of friction is equal to mu times Fn. Okay, I have the force of friction, okay, and I can plug that in. I'm trying to solve for mu, that's my coefficient of friction, which means that in order to use this equation, I also need to find Fn. And I don't actually have that written down on my paper yet. The only thing I have on my page right now about Fn is that it exists, and that it's equal and opposite to Fg. So I have a normal force, but I don't have an equation to find normal force. I do, however, have an equation to find Fg, and I know that Fn is equal in magnitude and opposite in direction, so if I find Fg, I will have found Fn. Again, if you're trying to find normal force, this is normally how you go about doing it. Fg is equal to m times g, which means it is equal to 22 times negative 9.8, and 22 times negative 9.8 is negative 215.6. Okay, and so negative 215.6 is Fg. Fn is positive 215.6 because it's in the positive direction. So my force of friction is 152 newtons. It is equal to mu times Fn, which is 215.6. Okay, again, technically when I wrote this, I said it was negative, but I'm going to tell you right now, you can't get a negative mu. It does not have direction like that. It's scalar. So I can drop the signs here, or you can drop them at the end, because if you divide it without doing that first, you're going to get a negative. You're going to need to drop it. All right, to isolate this variable, I need to divide both sides. Those are being multiplied. So we're dividing both sides by 215.6. So 152 divided by 215.6 is 0.70500. It keeps going, but it says to give at least 3 decimal places. So let's go ahead and do that. 0.705. There we go. Number 8. Number 8 says, the free body diagram below shows the forces acting on a ball. And we're just going to answer the questions that go with it. Net force. Okay, well, net force here is going to be 0. 20 newtons up, 20 newtons down means that I don't have a net force. Those all cancel. The free body diagram is an example of balanced forces. The acceleration is 0 because they are balanced. I have no net force, therefore I have no acceleration. Which direction could this object be moving? It could be doing any of these. It could be moving up, down, left, right, or not moving at all. All I know about this object is that it's not accelerating. It could be moving up at a constant speed. It could be moving down at a constant speed. It could be moving left at a constant speed. It could be moving right at a constant speed. Or, because it's not accelerating, it could also be stationary. Okay, it just wants to know what it could be doing, and I don't actually know which direction it's going. I only know that it's not accelerating. Next question says, suppose you exert 250 newtons of force on an 18.2 kilogram crate and push it across the kitchen floor at a constant velocity. What is the force of friction that acts between the crate and the floor? This appears at first glance to be a calculation problem, but it's really not. And the reason I say that it's not is because of these 2 words, constant velocity. If you have an object moving at a constant velocity, it means that your forces are balanced. It means that they cancel. I have no net force, and therefore I have no acceleration, and that's how I'm moving at a constant velocity. And so if I am pushing something with 250 newtons of force, that means that the force of friction opposite the direction I'm pushing would also be 250 newtons. It would look like this, where you have a free body diagram with forces that are balanced. My force of friction would be equal and opposite to my applied force, and so that's the only way you end up with constant velocity. So your friction would be 250 newtons in the opposite direction as the force that you exerted. Next question says, Isabel pulls a 6-kilogram cart, causing it to accelerate from rest at a rate of 17.45 meters per second squared to the right. If the coefficient of friction between the cart and the floor is 0.281, what is the force of friction acting on the cart? All right, I need a fresh sheet of paper so that we can work this out. All right, so it's accelerating to the right due to the force that she's applying to it. So I know that I have Isabel pulling this cart with an applied force that's going this way. It doesn't actually tell me what her applied force is. It just tells me what the acceleration is. I know that there is friction. Because I have a coefficient of friction, there will be friction in the opposite direction. So I have that. I know that this cart is on Earth, and so I know that I have Fg, and I know that this cart is accelerating in the horizontal direction and that nothing is happening vertically, no acceleration or anything, and so my vertical forces need to cancel each other out. They need to be balanced, they need to be equal and opposite. So that's my free body diagram without any numbers on it at all. Let's go ahead and see what numbers we can add, because I can't actually solve for anything right now without knowing a little bit more. I don't have an equation for Fa or Fn. I do, however, have equations for Ff and Fg. Fg is again weight. It is mass times gravitational acceleration. And I do know both of those pieces of information, so I can solve for the weight right off the bat. Force of friction has an equation of Ff equals mu times Fn. And I know mu, it's in the question, but I don't know Fn yet, so I can't use this yet. So let's start with the one we can use. Fg equals mass times gravitational acceleration. The mass is 6. Acceleration due to gravity is 9.8. Again, technically it's negative. I'm going to add that on afterward. 6 times 9.8 gives me 58.8. And so Fg is 58.8 newtons downward. Fn is 58.8 newtons upward. Again, I've already determined that those are equal and opposite to each other. So now I said I couldn't use this equation yet because I didn't know Fn. Now I do. Again, if you draw the diagram, start solving for what you can, and you can probably find your way to the next part. Ff is mu times Fn. So Ff is equal to, mu is in the question as 0.281. Fn is 58.8. And so we can simply multiply those values. 58.8 times 0.281 gives me 16.5228. And that will be my force of friction. You can round it if you like. By the way, it does tell me on here that I need to use a sign. That friction is in the negative direction. I don't get a negative number, but if I look at my diagram, I know that it's negative, because if I'm accelerating to the right, this is to the left. Okay, 16.5228 newtons. Direction, left. All right. Second question, what is the applied force acting on the box? Okay, applied force, I don't have a formula for. Okay, but if you're trying to solve for a force, and looking at this diagram, now I actually know a lot more than I did before. Let's go ahead and add friction to it. 16.5228 2. I'm just going to round it to fit it on the page. Okay, I don't have a formula for this, but I know everything else in my diagram. Okay, so if that is where you're at, you're going to want to see, can I solve for net force? Because you do have an equation for net force, not just a diagram that you can read to figure it out, but also m times a. And if you can find net force and you know the other forces on here and you're just looking for one, you can figure out what that force is. Okay, so looking at this question, it tells me the acceleration and it tells me the mass. The mass is 6 and the acceleration is 17.45 meters per second squared to the right. So let's go ahead and multiply that out and get our net force. 6 times 17.45 gives me a net force of 104.7, and again it is going to be newtons to the right. So F net is 104.7 newtons, and again it will be in the same direction as my acceleration to the right. You can also label that positive on here because that's what we've been doing. But the question doesn't want the net force, it wants the applied force. However, if I know the total forces acting on it, and I know this one, I can find this one. Same way we've been doing it, because F net isn't just equal to MA, F net is also equal to the sum of the forces. That means the forces to the left plus the forces to the right. I can also do this same equation vertically, forces up plus forces down. But in this case, those are already 0, so let's go ahead and just deal with the x direction. Okay, so F net in the x direction is 104.7 newtons to the right. Again, I'm just going to use a positive for the right. Equals forces to the left, I've got one. I'm going to use a negative sign in front of it to indicate that it's to the left. These are vectors, they need signs. Negative 16.5, and again, I rounded this, so I'm going to write the whole thing. 5228 plus my force to the right is FA. That's my applied force. That's what I'm looking for. Again, if I want to solve for this, I need to get this over here. Right now, I'm adding this negative number. So I need to subtract that negative number, or again, add 16.5228 to both sides. That's going to cancel it here. And in my calculator, I'm going to do my 104.7 plus 16.5228, and I get 121.2228, and that will be my applied force. So applied force, 121.2228 newtons. And again, it is to the right. Question 11. Below is a picture of a guy. Let's imagine he is in an elevator that is traveling down at constant velocity. Make the free body diagram with the options below. We talked about some elevator questions in class, and when we did those elevator problems, the only forces that we needed to consider were forces that were in a vertical direction. So let's go real quick and get rid of the left and right. There is no force to the left. There is no force to the right. All right. Now we can deal with just the forces that are present. Let me do that so I can see the boxes. Okay, which is up and down. Okay, if you have acceleration, well, first of all, let's label the forces. Upward force acting on this guy in the elevator. There is an up force. That up force is the normal force. It's the floor pushing against his feet. Okay, there is a down force. That down force is the force of gravity. It's the pull of the earth on the guy. Because the question says that he is moving at a constant velocity, you can still see those words even though this doesn't fit super well on my screen. Those words are still there. Because it says constant velocity, these forces have to be balanced. So I need to choose that this is equal to the down force and this is equal to the up force. However, if the question had said anything about acceleration, then I would have needed to make sure to specify my answers for the relative size in order to end up with the net force in the correct direction. But in my case, I should be good. They're equal. This is question 12, and it is the last question of our assignment. It says, a teacher moves a 14.7 kilogram desk across the room by applying a positive 193 Newton horizontal force. We're going to call mu 0.44. That's my coefficient of friction. And I am asking you to find all these things, Fg, Fn, Ff, and acceleration. All right. So in order to help us with this, let's see if we can start by just drawing a free body diagram. Okay, so I know that, and I already have kind of a picture up there, but I know that I have the desk. I know that the force of gravity, always a good place to start. The force of gravity is acting on that desk. I know that that desk is just moving horizontally across the floor. There's no acceleration or anything like that, no net force in the vertical direction. So I know that Fn and Fg are equal and opposite. I know that the teacher applies a positive 193 Newton horizontal force, and in the picture they've already even drawn that for us. That is this force that is going off this way to the right. That applied force, Fa, is equal to 193 newtons. And I know, because there's a coefficient of friction provided to me, that I'm going to have some amount of friction. So that's what I have in my diagram. We're going to be finding all these pieces anyway, so let's start with the ones that we have formulas for. And Fg is almost always the easiest one to start with, okay, because I don't have a formula for Fn, and so although I do have a formula for Ff, I'm not going to be able to get there without figuring out this first, and so let's start here. Fg is m times g. My mass in the question is 14.7. Gravity is, of course, 9.8, technically negative 9.8, but I'm really just looking for the magnitude so I can label it on my picture. 14.7 times 9.8 gives me 144.06. So this is 144.06 newtons downward. This is 144.06 newtons upward. So I've already found two of them just with that one calculation. Okay, I can find Ff because Ff is mu times Fn, and I just determined Fn, and mu is in the question. So force of friction, mu is 0.44, Fn is 144.06. So I'm going to take the answer and I'm going to multiply it by 0.44, and I'm going to get 63.3864 as my force of friction. Let's go ahead and add it to my diagram. 63.3864. Trying to write that a little neater. All right, so let's go ahead and fill in what we can. Fg. Fg is 144.06 newtons downward. I'm going to call that negative 144.06. Fn is 144.06 newtons upward. Ff is 63.3864, and I could have rounded this to 63.39, and that would have also been fine. However, I forgot one thing. Ff is to the left, so let's go ahead and call that negative. And then the last question is to find the acceleration of the desk. And again, the only equation that I have with acceleration in it, in this unit, is F naught equals ma. So I can find my acceleration so long as I have a net force and a mass. My net force is the sum of my forces. Again, vertically I don't have a net force, so I just need to find my horizontal net force so that I can plug it in here and then use that along with the mass to find the acceleration. Again, net force in the horizontal direction is just forces to the left plus forces to the right. That's it. Okay, so I have to the left negative 63.3864 plus my forces to the right 193. That's it. Again, keep in mind these are vectors. Make sure that you count that as negative when you're adding it, because technically you're subtracting. Okay, so if I do this, I have 193 minus, effectively, that number. and I get 129.6136. Now that's not my answer. That's not acceleration. That's net force. So let's go ahead and list it over here. 129.6136 equals, the mass is in the question, 14.7 times A. So now to solve for acceleration, I just need to divide both sides by 14.7. That'll cancel this, and that of course will give me an answer over there. When I divide by 14.7, I get an acceleration of 8.82, if I round that, meters per second squared. And again, it will be in the direction of my net force, which means it will be to the right. That is the last question on the assignment 301.4. So hopefully we answered all of the questions you may have had. But again, please make sure that you're asking if you need additional help.